Good afternoon, everyone. Thank you so much for all of you who are still with us following the virtual symposium after a very exciting morning with two incredible sessions. I am now honored to introduce two speakers in the session that we called the adult session. As a pediatrician, of course, I always look for data in the pediatric world, but this is a platform that can be totally used for adult as well. And so the first speaker will be Professor Wolfgang Bethge from Tübingen, and he's going to talk about his own experience with αβT-cell CD19 B-cell depletion in adult patients. And after, we will have Robert Lowsky, who is a professor of medicine in the BMT program at Stanford Adults. And he will mainly show us an overview of the vision about T-cell depleted transplantation at Stanford. So without any further ado, I'm going to leave the floor to Professor Bethge, and please, and thank you so much for being here with us.
Hello, good afternoon, everyone. First, I would like to thank Alice and all the organizers for inviting me to this really very stimulating meeting. And I'm very happy to share with you our adult experience with the alpha-beta T-cell depletion in the haploidentical transplantation setting. As A.I. Reisner earlier today nicely summarized to you, we came quite a way with our T-cell depletion approaches based on the early experience with CD34 selection at the end of the last century, nowadays moving forward to CD3, CD19, and finally to the TCR alpha-beta CD19 combined depletion approach. And we are currently continuing this journey to a further adoptive immunotherapy, namely the just discussed CD3045, our ADLI approach. Technically, also, the development did not stop, and you see on the right here some pictures from the newer technical platforms we use for this depletion approaches. And the principle is always an immunomagnetic selection of the graft in vitro prior to transplantation and retransfusion into the patient, which is done under GMP conditions, under very controlled production and manufacturing restrictions, but which is nowadays possible in on-site GMP facilities with the new technical equipment and the very thorough in-process controls we have there. This is not so much from the experience, or no longer so much dependent on the experience of the individual centers. This TCR alpha-beta approach is always in our center used combined with CD19 depletion to prevent lymphoproliferative disease after transplantation. And we'd like to ensure a graft which has still a lot of gamma delta positive T cells in the graft, but also a lot of NK cells and progenitor cells, which we think, as already mentioned today, the transplant is a mixture of different cell population, and engraftment and immune reconstitution not only depends on the CD34 component. What I show here today is the adult part of a multi-center open-label single phase 1/2 study, which was sponsored by Miltenyi in Germany and one site in the Netherlands. We enrolled up to 60 patients into this trial, 30 pediatric and 30 adult patients. And the manufacturing was happening decentralized in 7 GMP sites throughout Germany and the Netherlands. And the main aim of this study was to show safety and feasibility in a multi-center, multi-production site setting. And this was measured by the primary objective, which was the incidence of grade 2 to 4 acute GVHD on day 100. We present here data with a 2-year patient follow-up. And you see here the centers which have been involved in blue all the clinical trial sites, and the manufacturing centers are depicted in red. And a few centers had no opportunity or no GMP production site for graft depletion, which we then supplied with a depleted graft from Tübingen. This now highlights the separation results in the adult part of this trial. So the 30 adult patients, you see here there were 45 adult donor depletion procedures. Some donors needed 2 depletion procedures. In some it was only one. You see how robust this depletion GMP procedure can be done in a multi-center setting, as you see that the variability of the graft is very narrow, very close together. We had no excess T cells in the graft, alpha beta positive T cells in particular, and the depletion efficiency was very high. And here, just to illustrate the pureness of the graft, you see here the content post depletion was purely gamma delta positive T cells and almost no alpha beta positive T cells. The patient demographics are depicted in this table. You see the median age of this patient cohort was 38.5 years, ranging from 20 to 63 years for the oldest patients, mainly acute leukemia. In particular, in the adult setting, it's AML, but also some other hematologic malignancies were transplanted in this study. About 2/3 of the patients were in complete remission at the time of transplantation, and 1/3 only were non-remission patients. But for quite a substantial proportion, this was the 2nd or 3rd transplantation. So we are looking at a very advanced patient population, which was treated in this study. As donor, we used haploidentical relatives of the patient, either children or siblings or parents of the donors. In 2 cases, cousins were used. And the median age of the donors was about the same distribution as the patients treated. So the age range was very close together. This is our transplant protocol. It's built on a reduced intensity conditioning consisting of fludarabine, tiotepa, and melphalan. And it was the same conditioning and the same protocol for adults and children. We use a dose of a pre-dosing with ATG gravalon, so ATG Fresenius, in a total dose of 30 milligrams per kilogram, very early prior to transplantation. So it's placed on day -12 to day -9 prior to transplantation to allow the lowest possible levels of ATG in the system at the time of transplantation. We did some pharmacokinetic studies of ATG to find the right placement and decided to move it to a very early phase, not to deplete actually the incoming graft further, and just to ensure the engraftment. It's merely a treatment of the patient and no prevention of GVHD. It's more treatment or reducing the level of immune response in the patient himself. The graft was followed by a short course of MMF for a total of 30 days, which was based on our earlier experience in the CD3, CD19 setting, where we saw that we see some early GVHD if we drop immunosuppression completely. And we can talk later on about whether this is actually necessary with this protocol. Our cell dose targeted was at least 4 × 10⁶ CD34 positive cells per kilogram body weight. And we did allow up to 25,000 alpha positive T cells in the graft. And also the CD20 target was below 100,000 cells per kilogram. For a few patients in the protocol, especially in the adult part, we omitted the ATG completely and replaced it by total nodal irradiation at 7 Gray on day -1, which was kind of a pilot for developing an ATG-free protocol. And we could see in the adult part, at least, that the TNI is very safe and very efficient to omit the ATG. This was used in only 5 adult patients, only the one which advanced disease. We thought that the possible reduction of the graft versus tumor effect by implementing ATG in the protocol could be benefit from the use of TNI in this setting. Within the protocol, we saw with the initial dose of 50 milligrams per kilogram body weight ATG Fresenius, especially in the adult, in the pediatric setting, where there always also non-malignant diseases have been enrolled, a higher incidence of graft rejection than we expected. And therefore, we amended the protocol after about 20% of the patient to a higher dose of ATG, which was then used for most of the adult and pediatric patients. It was 30 milligrams per kilogram body weight, as I already showed you in the trial overview. This was the graft composition in this study. You see, we could ensure engraftment with a dose down up to 4 times 10 to the 6 CD34 positive cells. In a median 8 times 10 to the 6 CD34 positive cells have been transfused. We could stay with the target to have less than 10,000 alpha-beta positive T cells in the graft, but we have a large amount of gamma delta positive T cells, and in particular NK cells in the graft, which was our aim to benefit from the immune reconstitution and the graft versus tumor capacity of these 2 cell components or graft components. You see that engraftment in this setting is very swift with a very fast recovery of both neutrophils and platelets in a median of about 13 to 15 days after transplant. Final engraftment was achieved in all of the patients. In 2 patients, so 7% of the patients, we, however, observed initial graft rejection, which were then reconditioned and received the second donation graft, which then rescued these patients. So unfortunately, we did not lose any patients due to non-engraftment. Acute GVHD was very low. We did not observe any grade 3 to 4 GVHD in this trial. We observed a moderate grade 2 GVHD, mainly confined to a flare of skin GVHD, which was very controllable with a short course of steroid in 17% of the patients, so just 5 patients. There were some grade 1 GVHD, which was also a little rash, mainly with engraftment, which we did not treat at all. So only 5 patients really had a short course of steroid for treatment of skin GVHD. Chronic GVHD was a little bit more pronounced because it was observed on a later stage when we had, again, alpha-beta T-cell reconstitution to some extent, but which was only severe in 3 cases and moderate in most of the patient. And the total rate of GV 32% is still very moderate if you compare it, for instance, to a standard matched and related transplant. How was immune reconstitution with this approach? You see here the CD4 counts in red and the CD3 counts in blue at different time points after transplantation, the counts of alpha beta and gamma delta positive T cells, and the B cells and NK cells. And you can observe that there is an initial flare, as we often in this T cell depleted setting observed after haploidentical transplantation of NK cells, which I think is a benefit, especially in patients which are treatment refractory or with remaining disease burden. We see also that although we merely have a transplant with only gamma delta positive T cells, that the alpha beta positive T cell recovery is very fast and regains and overpaces the gamma delta T cells around day 100. However, we still see that the CD34 counts are recovery more swiftly than after CD3 and CD19 or CD34 depletion, but still lag a little bit behind if you compare it to an undepleted graft. So we need about a year to obtain levels above 200 CD4. What is about infectious events? You see here that we had 2 CMV infections in the adult cohort and 2 adenovirus infections. We had no losses due to viral infections. We had also some fungal infections and septicemias, but the treatment-related mortality, the non-relapse mortality, was only 17%. So it was very low, given the high risk cohort we are treating here, with having 1/3, the second or third transplantation, being heavily pretreated and not in remission. Viral reactivations were frequent, with about 50 to 60% CMV reactivations and a very low rate of adenovirus reactivation, which is not a problem really in the adult cohort at all. So we had no treatment refractory CMV reactivations and no cases of CMV disease. You see here the causes of death. We lost 9 patients after transplantation in this 30 patients I report here, most of them due to relapse and some to some intensive care problems and one case of bronchiolitis obliterans and pulmonary problems, multi-organ failure, but as you can see, no real infectious death. If you look now at the outcome, the overall survival in this cohort of 30 patients at 2 years is 70%, which is excellent for this high-risk patient population. Also, the disease-free survival is with about 60% very promising, and a very interesting endpoint is the GVHD-free relapse-free survival rate, which is also at 45%. If you compare leukemia patient in this cohort, leukemia and MDS, we lump together and compare the patients who have been in CR or not in CR at the time of transplantation, you can see that the survival curves merely overlap. So the relapse incidence in non-remission patient was also very low, which might be one of the real benefits of this kind of transplantation approach due to the fast NK cell recovery and the also proven graft versus tumor effects of gamma delta positive T cells. We think that this approach is particularly suited for non-remission patients. But I don't want to not present also the whole cohort of patients. So here are a few slides showing also the pediatric part of the study. If you look then the total of 60 patients with a median age of 18.5 years, ranging from 1 to 63 years, you see that clearly with the pediatric cohort, there are then more ALL patients coming into the patient population. In the pediatric part, we This was merely a basket study for entities, and the pediatric investigators decided also to include some solid tumor and non-malignant disorders within this trial. So this is a mixed bag of diseases were transplanted in the whole cohort. About 2/3 again was in complete remission, but you see here an even higher proportion had advanced disease with second or third transplant. And now side-by-side comparison of the survival curves of adults and children, and you see, which was also very astonishing for us and might be merely a matter of patient selection, the adults actually outpaced in the results the pediatric part. So we had very robust results also in the children, but due to the very advanced patient and especially also the solid tumor patients included, the results in outcome was a little bit worse in the pediatric part. Treatment-related mortality in the pediatric population was about the same as in the adult population. And if you look at the overall disease-free survival and graft GVHD-free, relapse-free survival curves of the whole cohort, you see it's a little bit lower than in the adult part of the study, but still the results given the high-risk cohort we are treating here seems to me very promising and reassuring. So what do we plan next? We just heard in the last session the very exciting data from Michael Machin in Moscow, and we would like to base in the next step also in the adults, but also it's again a joint protocol with adult and children centers within Germany, a multi-center study building on our backbone of TCR alpha-beta depletion and adding back in a dose-escalated manner 3 dose levels of CD45RA depleted DLI after transplantation on day 30 after transplantation to foster faster immune reconstitution and having the hope to even improve the still delayed T-cell reconstitution after transplant without an increased risk of acute GVHD, since we really like the idea of having a transplant where you have no immunosuppression afterwards and have also a very good platform for any adoptive immunotherapy afterwards in case of disease relapse. So I would like to conclude my talk with the summary. We could show with this study that TCR alpha-beta CD19 depletion is feasible in a multi-center fashion, also in a multi-center GMP production setting. The grafts are very robust and quality assured and can be automatically produced in different GMP sites. We saw a very low rate of acute GVHD and a low rate of chronic GVHD, and in particular, we did not lose any patients to acute GVHD. We saw an excellent non-relapse mortality if one compares what we have seen with other haploidentical approaches, with only 17% overall after 2-year follow-up. And we see an excellent disease and overall for disease-free and overall survival, although we treated a very high-risk advanced patient cohort. And especially in the adult, we saw overlapping curves for non-remission patients in this trial. So we think that this seems to be a very effective platform to offer also patients at transplant who are not in remission at the time of transplant. To be honest, I don't think that we need at all any post-grafting immunosuppression with this approach. We still kept the MMF backbone also in the new protocol, since we want to compare immune reconstitution data of the previous study with the new study. We thought we'd not change anything apart from the adoptive DLI, but I don't think with this low rate of acute GVHD, the MMF would be really necessary. It will be also very interesting to build on our experience with the few patients we did the 7-grade TNI, which might be an excellent protocol, especially in the adult part of the study, to assure engraftment without ATG in the protocol. Our pediatric colleagues, however, have always some problems with using irradiation in the protocol because of the potential negative effect on a growing infant. In the adult part, this would be, in our experience, very little impact. For instance, we use also this TNI approach for any retransplantation. So the patients who have been rescued, who had non-engraftment after the initial haploidentical transplantation, were most of all reconditioned with fludarabine TNI. And with that, I would like all the collaborators of the studies, all the collaborating centers, and especially also Miltenyi Biotech for supporting this study and for being a sponsor on this trial. And in particular, Rupert and Grettinger, who was the lead PI for this study, which we will also hear tomorrow in his presentation on the future of haploidentical transplantation. Thank you very much, and I'm open for any questions.
Professor Lowsky is a professor at Stanford University in our blood and marrow transplant program. He has extensive experience as an academic clinician and medical researcher in hematopoietic stem cell transplantation for over 30 years, with broad experience and expertise in the field, particularly in trials involving graft engineering and immune tolerance. He has designed, written, and implemented many single and multi-center studies, including those funded by CIRM and the NIH, and has served extensively on our Stanford IRB and SRC in cancer-oriented trials. Dr. Lowsky, it's a privilege to introduce you today.
So title is Graft versus Leukemia Without Graft versus Host Following Allo Transplant. I have no disclosures relevant to the presentation. However, looking at my self-image in the Zoom, my only disclosure is the office admin uses my office as storage, as you could see behind me. That's about it. Four sort of main topics of conversation, some introductory sound bites for today's presentation. Then I'll show a series of slides on models of graft versus host alloreactivity and BMT. Our program's bench to bedside translation of preclinical models to clinical trials, and then some consideration for future approaches. By way of introductory soundbite, it's all about allogeneic hematopoietic cell transplantation, cells from a donor, and this is in context strictly of leukemia. I put a red line through lymphoma because lymphoma now has moved into the realm of CAR T cells, predominantly, for all the right reasons. And lymphoma cells act as their own antigen presenting cells and are very efficient, or can be efficient, at inducing graft versus host alloreactivity, whereas leukemia cells are different. They are not efficient antigen presenting cells, and I'll show you that in the models. The infused donor T cells, as everybody knows, provide several important functions. They facilitate donor cell engraftment. I think I have a pointer. They protect against infections. They induce the deleterious, harmful immune-mediated graft versus host reactions, graft versus host disease. And then they, at the same time, induce beneficial immunologic rejection of the underlying leukemia in a process we call graft versus leukemia reactions. That GVL has been recognized for decades, is well known. It's very important at reducing the risk of leukemia relapse after transplant. And despite it being known and studied for over 30 years, there's little consensus on what cells are truly responsible for GVL, other than the fact that the infusion on typically day 0 of post-thymic donor T cells are clearly involved. there's little consensus likewise on what are the targets and structures recognized on the tumor cell that lead to graft versus leukemia reaction. What is known, however, is that the risk of leukemia relapse is intertwined with the degree of GVH, graft versus host alloreactivity. This is shown in Mary Horowitz's 1990 landmark paper in Blood. On the y-axis is probability of relapse. On the x-axis is months after transplant. And what you see is here in an identical twin, genetically identical twin transplant, where there's virtually no graft versus host alloreactivity, there's a very high risk of a disease relapse. And the main mechanism of cure here is all dependent on whatever the contribution is from the transplant conditioning. If the recipient receives graft depleted T cells, likewise, there is a very high level of tumor relapse. If a patient undergoes a traditional transplant, but there's no clinical evidence of graft versus host, there's also a considerable risk of disease relapse. And the only patients who have a very low risk of disease relapse are those who have clinical manifestations of graft versus host alloreactivity. So there's no question that the beneficial GVL reactions are intimately wrapped up with the harmful GVHD activity. And the conundrum really is, how do you unravel these two reactions? And I'll say, I put down an important distinction because it's all alloreactivity. And when it occurs in the lymphohematopoietic space, in the bone marrow, the blood, and lymph nodes, you can call that GVL. And when the same alloreactivity occurs in the target organs of the skin, liver, and gut, that's what we call GVHD. The next series of slides will show some conceptual blueprint of alloreactivity. And what I show here is that direct antigen presentation by a host cell, whether it's a host bone marrow cell, a host leukemia cell, or a host parenchymal tissue cell. This provides a very inefficient donor graft versus host activation. And what you see on the left is a cartoon of naive donor T cell that's infused on day 0. I wrote naive because that has a very broad TCR repertoire, whereas the memory T cell compartment has a very narrow T cell repertoire and is much more limited in its ability to be engaged. So you have the host tissue cell, a parenchymal tissue cell, bone marrow cell, leukemia cell. Generally, these have low level of class 1 expression, do not express class 2, do not have any co-stimulatory molecules on them. And if it's a tumor cell, often they could have inhibitory molecules like CTLA4 or PDL1L on their surface. So these cells consequently don't really stimulate much of an immune response. And I said earlier, the lymphoma cell is different. That's like an antigen presenting cell and behaves more like these cells shown here. What really drives alloreactivity, graft versus host direction, after a transplant is antigen presentation by the host APCs. And I show you 3 cartoons in this slide. At the top, you have a host antigen presenting cell, has high expression of class 1, class 2, and co-stimulatory molecules. And in context of HLA matched, what's going to happen is polymorphic minor histocompatibility antigens are uploaded into the class 1, class 2 molecules, and these will engage the naive donor T cells to induce effector function. And if the minor histocompatibility antigens are those that are expressed on hematopoietic cells, well, then you're going to get more robust engraftment and graft versus leukemia activity. And if the minor histocompatibility antigens uploaded by the antigen presenting cells really are tissue specific, then you will get more graft versus host. Here is the MHC mismatch, the haplotransplant setting. And here, basically any polymorphic peptide that's a minor histocompatibility antigen, any polymorphic or even any monomorphic, same as self, same as the donor. As long as it's uploaded into a non-self MHC, that will stimulate an immune response. So much more alloreactivity once you're going beyond MHC matched. And what I show in the bottom panel is sort of what we see in transplant, where the recipient undergoes myeloablative conditioning or reduced intensity conditioning. There's cell death, apoptosis, release of intracellular peptides and antigens into the extracellular matrix floating around. And then sometimes these are absorbed onto class 2 molecules, which then are exogenously presented to CD4 T cells. And sometimes some of these extracellular peptides are engulfed, processed, and chaperoned to class 1 molecules. And this would be endogenous antigen cross-presentation to CD8 T cells. And this does induce a robust response. It's unknown, it's 4 weeks, 8 weeks, 12 weeks after transplant. The host APCs are replaced by donor APCs. And by that time, the tissue inflammation, all the damage has been repaired. So there's not a lot of peptides floating around in the extracellular matrix. Lymphocyte recovery has been established, so there's no drive for any T cell that's being engaged to undergo homeostatic proliferation. The donor APCs, they can't, they're only presenting self-polymorphic minor histocompatibility antigen to self, so it won't stimulate much of an immune response unless there's some gig available to pick up peptides and do cross-presentation. And then just summarizing what I said in the last few slides, T cells infused on day 0. We're talking predominantly about the naive CD4, CD8 T cell compartment. And if these donor T cells are stimulated by host APCs to a bone marrow cell, minor histocompatibility antigens, or leukemia cell, tumor-associated antigens, you get GVL. And if it occurs in parenchymal tissue, then that's GVHD. This next series of slides will show our division's bench-to-bedside translation of preclinical models of bone marrow transplant that separate GVHD from GVT to establish proof of principle that scientific approaches can be used to treat human diseases. This first model evaluates and showed that regulatory T cells can suppress GVHD yet allow graft versus tumor reactions. And what you see on the left-hand side of the screen, and this is a mouse model of bone marrow transplant. It's a class 1, major minor mismatch, so your worst case scenario. And the recipient mouse undergoes total body irradiation, and the donor mouse gives a T cell depleted bone marrow transplant, no T cells. And you'll see on the y-axis is % alive, x-axis is days after transplant. If you do T cell depleted bone marrow, you rescue the animals and there's no GVHD because there's no T cells. If you then repeat the experiment and add splenocytes, conventional T cells, at some dose, you get death from acute graft versus host disease. And that's showing the massive proliferation in bioluminescence imaging in this mouse over here. And then if you repeat the experiment a third time, use T cell depleted bone marrow, T-con at the same dose that resulted in death from GVHD, but you add a non-physiologic ratio of Treg, a 1-to-1 ratio. You can go maybe as high as 1-to-3. Everett would know better than I. You get protection from GVHD. So that shows that Tregs do suppress T-con activity. And then if you repeat the same experiment, but in addition to doing that, you add tumor cells after you give the TBI, not before, otherwise you kill the tumor. So on day 0, you infuse, sorry about the background from my email. I don't know how to turn it off. But if you give T cells, the combinations that we just discussed, and lymphoma cells, if you give just bone marrow, T cell depletion, and tumor cells, all animals die from tumor progression. If you give splenocytes and tumor cells, all animals die. There's no tumor progression, they're dying from graft versus host. But if you do this 1-to-1 ratio of Treg to Tcon, there's no GVHD, and the Tcon were still capable of inducing meaningful graft versus tumor reactions. Thereby, that is a separation of GVHD from GVT. And over the years, through a variety of protocols, this was translated to clinical trials. This one we called Protocol 236. This is a 1-to-1 ratio of Treg to Tcon. And what you see here is, here's the patient, undergoes myeloablative conditioning. And then the donor graft, G-mobilized graft, is CD34 selection beads. And from the flow through, then it's, that would be called Tcon, even though it's mixed with B cells and monocytes and NK cells, whatever is the flow through. It's dose adjusted to pull out 3 million per kilo of Tcon with whatever cells it comes with. And then from the rest of the flow through, there's a isolation procedure, like a high-speed cell sorting, to isolate CD4, CD25, positive CD127 low, FOXP3 Treg cell. On day 0, the fresh CD34 Tregs are infused. The doses are shown here. And then 2 days later, Tcon is infused. And it's just single agent, low dose prophylaxis with tacrolimus. And 37 patients have been treated on this type of a protocol. There's very low acute GVHD. So yeah, it's a nice recapitulation of the animal model. And it's hard to be dogmatic about what's going on with tumor relapse, but certainly it's not any more than what you would otherwise see in a traditional transplant. There's nothing done here to enhance GVT, GVL, but it's not minimized by this low dose of T cells and the absence of GVHD. The 1-year GRIF is 77%. In a similar type of trial, this technology has been picked up by a commercial entity called Orca. And Orca conducted a multi-center trial. This is all HLA matched, by the way. And in here, it's the same idea. It's a 1-to-1 ratio of Treg, but instead of giving Tcon, it's slightly Orca modified, which I'll explain. Okay, it's the same. It's myeloablative conditioning. It's the host, G-mobilized graft, selection column to enrich CD34. From the flow through, that then undergoes a CD45 RA depletion. So you remember we said earlier T naive. So this gets rid of the naive T cells, and you have total memory. You have B cells, NK cells, and monocytes. And from there, it's dose adjusted to give total T memory 3 million per kilo. And after you get the rest of the flow through, they isolate fresh Tregs. And then it's essentially a very similar template to what's shown in the previous slide with single agent prophylaxis. And just like before, the Orca graft in a multi-center trial has also a very low rate of acute GVHD, and is also got a very excellent 1-year GRIFs rate, which suggests a very low tumor relapse rate. This kind of work is now going to be expanded to include haploidentical donors with a very similar type of platform to be used. More to come on that. Another model that we've developed at Stanford, similar but different, is, again, I'll just show you the model. It's a major-minor mismatch, strain A into strain B, where the recipient undergoes myeloablative TBI, and then just after the radiation is infused with a lymphoma cell line, and then they're infused with T-cell depleted bone marrow to get hematopoietic recovery, and then either all the subsets of T cells, total T, total naive, total memory, that'd be like an ORCA, or even subsets, CD4, CD8 subsets of naive and memory. And then you monitor for tumor growth and graft versus host. And sort of a summary slide of it is shown here in the right-hand part, percent alive on the y-axis, days after transplant. And basically, it shows that animals are dying either from graft versus host or tumor progression if various subsets are given. But the only subset that had absolutely no GVHD and still provided anti-tumor reactivity was not total memory. That still caused a little GVHD, but CD8 memory T cells. And I put it's sort of a mystery as to why would CD8 memory T cells provide GVL reactions. The easiest answer, and it's all made up because when you don't have the answer, you're allowed to say whatever you want. You could say it's molecular mimicry to whatever pathogens the donor mouse or whatever memory they've evolved. There's some kind of molecular mimicry going on to the tumor cell line. Over the years, we've had three clinical trials, three themes of clinical trials using CD8 memory T cells for a total of 39 patients. In the first generation of the trial, it was only for patients who relapsed after an allo transplant, HLA matched and a sibling donor. And instead of treating with a DLI, an unmanipulated DLI, we treated with CD8 memory. The numbers of cells were between 5 to 10 million per kilo. So about 1 × 10⁷ or just under 1 × 10⁷ per kilo. And just as effective at DLI for tumor control, about 20 to 25% long-term cures, so to speak. May be better because only 1 out of 17 patients got GVHD that was easily treated to resolution within a few weeks of steroids. So it did look like there was less GVHD. We had a second trial. This was to treat patients who after a non-myeloablative transplant had achieved only mixed chimerism, because there's enough literature to say mixed chimerism associates with an increased risk of relapse. So we thought, well, why don't we give, instead of DLI to convert from mixed to complete, let's give CD8 memory, see if it converts from mixed to complete, but without GVHD. And that trial was completed and it's being analyzed. And the short answer, unpublished observational, put it under that heading, is, yeah, it converts about 70% of the patients and there's no GVHD. And it's hard to say exactly till we finish analyzing, but it looks like those who were converted from mixed to complete had relapse rates that were identical to those who attained complete chimerism on their own early on. And then we have a third trial, which is very much like the Treg, T-con, or Treg, ORCA, T-naive depleted graft. It's same strategy. It's a myeloablative CD34 selection, and from the flow through, we do a CD8 memory T cell population with single agent prophylaxis, and that's ongoing, and it remains to be seen what happens from there. So the summary to this point is we do graft engineering strategies, and we've confirmed we reduce the risk of acute GVHD to less than 10%, and it appears to separate GVHD from GVT. And these are our three strategies that our adult program has been using. And at the beginning, you know, I sort of said, talked about CAR T taking over lymphoma. Well, CAR T has made the conversation a lot about how to reduce and minimize tumor relapse. And I think that's where we're going in some of our thinking is the main reason for an unsuccessful outcome after an allo transplant still is disease relapse, at least in adults. I don't know in kids. So now we want to bring in strategies to enhance GVL, but on this kind of a platform that mitigates GVHD. And we've done experiments and models here. Here's a model, and this is, I think Wolfgang made reference to this in his talk at the end. This is about donor immunization to tumor peptides to generate anti-tumor immunity. And this is an older publication, but it still was the backbone of our thinking. Here again is a major minor mismatch. And here the donor receives WT1 peptide injections weekly ×4, then undergoes a bone marrow harvest and splenocytes being added. The recipient gets TBI. FBL3 is a leukemia cell line infused after the TBI. And then there's also post-transplant host recipient tumor peptide immunization. And we did all these combinations. And in the bottom slide, part of the slide, you see that the WT1 tetramers reside in the CD8 memory T cells uniquely. And that here's some of the outcomes. If you immunize the donor only to incomplete Freund adjuvant, so no WT1, the animals die usually within 2 weeks of tumor progression. If you do only pre-transplant donor immunization with nothing post, there's good adoptive transfer of tumor immunity, but some animals, as you see here, within 3 weeks are dying from tumor progression. And the combination that worked best was the pre and the post immunization. Here the animals survived. If you followed the animals, there's no GVHD mitigation strategy in this model. By day 50, all the animals were dying in this strain combination from GVHD. So this is a photograph on the left. We tried exactly this with the FDA. Instead of WT1, we used PR1 as a peptide because that had been shown by an MD Anderson group and others that you can induce PR1 tetramers, and PR1 is expressed on leukemia cells and MDS cells. So there was about 400 patients had received, patients, not donors, had received PR1 peptide vaccinations, and it was known to be safe and stimulates an immune response. And you don't see the side view. This is about 3 inches thick of papers. That's when it was paper. This is 2009. Sam Strober and myself had, I don't know, at least 10 back and forth conversations over 2 years with so many resubmissions. But after 2 years of doing exactly what you saw in the animal model, we said we submit. The FDA said, no, not PR1, come back with a different peptide. And we could discuss, if anybody's interested, why the FDA didn't like PR1. It's too structurally similar to PR3, which is the peptide for Wegener's. Okay, so time passes. The sponsors of this symposium, they developed some kind of in vitro, commercially available closed system where you could generate WT1 specific CD4 and CD8 effector memory T cells. Okay, then let's maybe reinvent our thinking, reconfigure it to exactly the animal model or the last slide. And that's what we're working towards. And you could have a donor HLA matched or mismatched, unstimulated apheresis, goes through some commercially available closed system for WT1 effector memory T cell generation. Those cells are cryopreserved. And then the patient gets their transplant conditioning. They can get some kind of engineered graft. It could be alpha beta depletion. It could be an ORCA graft like this. And then shortly thereafter, the cryopreserved WT1 effector cells are thawed, infused, and then you give WT1 peptide vaccination to the recipient. The FDA is much more lenient to vaccinating a cancer patient than they are to vaccinating a healthy donor. And then you'd have all the standard outcome measures. And of course, you would follow WT1 specific CD4, CD8 effector memory T cells in the peripheral blood and see if you're increasing their or having persistence with post-transplant vaccination. I think that's it. And just thanking our group basically for the work that we've done over the years. It's all the clinicians involved and clinical scientists involved here on the left and the right. That's our group. It's grown over the years in the right direction. Radiation oncology, who's been very helpful, and our biostatistics group. And of course, CRC, that's clinical research coordinators. NC are our transplant nurse coordinators, and CTF is the cell therapy facility. Without any of these three groups, nothing would have been possible. Thanks.
This is great. That was another really interesting session. I don't see question typed in the Q&A chat, but please, everybody who would like to ask a question, do that. I would start in the meantime, and the first question is for Professor Bethge, and is about the use of MMF. On your conclusion, you said yourself that you don't think that is really necessary to use the MMF. Looking at your data, the quality of the alpha beta depletion was outstanding, and you really infused very few alpha beta T cells. I'm wondering if there is a window of residual alpha beta T cells that you consider at higher risk for developing GVHD, and so you would consider to maintain the MMF for those patients, while for the others would be better to not have any pharmacological immunosuppression.
I think this is a very good proposal. The problem is really how to study this in a prospective clinical trial if you have so many subgroups. So we would rather propose to stick to one protocol. We had a lot of discussions about ATG, about the MMF use. And for the next protocol, we would just out of comparison reason keep the same kind of protocol for the proposed next study to see whether the added benefit of CD45RA actually adds anything to the immune reconstitution, because this is the main problem in our view. I would actually think that it's, at least in our adult experience, it's no problem whatsoever to drop the MMF anyway, because if anything, what it does, it would lower a little bit the rate of the skin flare, which we see with engraftment and the early skin GVHD, which was clinically very manageable, and we had no problem of any like transition from acute GVHD early on to chronic GVHD. All the patients we saw with acute GVHD had a complete resolution of their GVHD. So there's, in my view, in the adult part, at least, no point of getting additional MMF.
Robert, please.
Thanks. I think I'm not on mute. Yeah. Wolfgang, I liked your talk. Maybe I misheard something, but I wanted to go back on it. Did you mention that the non-relapse mortality was 17%? That's what what were people dying from, and what would the non-relapse mortality be like in a standard of care for that, a similar type of patient population?
Perhaps I can share the slides again.
Tell me you showed it and I wasn't paying attention.
Yeah, that's no problem. The causes of death. So you see it here. It was.
Oh, I see. Yeah, but you said non-relapse
and no GVHD and no actual clear infectious events related to viral infections, at least in the adult part.
Yeah, that's what I was specifically honing in on, if it was death from viral infection. Okay. And then, okay, and what would you have thought would have been in a standard of care for this kind of a patient population? Something similar, higher, or? lower.
Treatment-related mortality, I would guess, in our experience, in just the same high-risk population would rather approach 20 to 30%.
Okay. So then that's significantly less. Thanks.
So there are two questions in the chat. One is about the rate of graft failure, either primary or secondary, Wolfgang, and the second one is about autoimmune hemolytic anemia. If you observed in this population any case of autoimmune hemolytic anemia.
Okay. So the rate of graft failure for the hematologic malignancies was 7%, clumped together pediatric and adult population, which was very similar to what we have seen in the adult part of the study as well. So clearly there is a risk of non-engraftment or graft failure. Most of the patients were actually then rescued with a secondary graft. We have seen that the graft failure rate was reduced by the increased dose of ATG. Initially, I think it was, if I remember correctly, in the range of 15%, which was then halved to 7% by the increased dose of ATG. And we did not observe any graft failure in the adult cohort with the TNI protocol. So clearly, I think it's a matter of the conditioning intensity and pre-treatment of the patient's immune system prior to the graft coming in. I think there is no point and no hint that actually the post-grafting immunosuppression plays any role in that respect. But this is clearly something we have to look into in a more homogeneous patient population, since in the pediatric part, where the first signals were seen that there is an increased rate of graft rejection, there were also some non-malignant diseases, and the one of the graft rejections in the adult cohort was only the sickle cell patient. So I think for these patient population, which are not heavily pretreated with chemotherapy, you need some perhaps even a little bit more intense conditioning.
Thank you. And
but we use for all the patients the same reduced intensity conditioning.
What about the hemolytic anemia?
To be honest, at least in my experience, we did not observe any cases of that. We have seen this in the regular setting of allogeneic transplantation, I would say more frequent than in the haploidentical setting. I don't know exactly if we actually collected data on such detailed event within the study, but at least in the about 25 patients we have treated in pediatrics and adults in Tübingen as part of the study, I don't recall any cases of that. Thank you.
Robert, can I ask you to comment a little bit about the use of pharmacological immunosuppression in your study, the ORCA study versus the, let's say, standard of care arm that you compare the data with?
Sure. Before I do that, I'm not certain I understood why was somebody asking about hemolytic anemia with alpha-beta CD19 depletion. Is there something known about that?
No.
Or a theoretical concern that
The question is coming from David Shire, who is an attending in our pediatric group. And we recently had 3-4 cases of hemolytic anemia, mostly related to in terms of time window with viral reactivation and start of B-cell reconstitution. So we attributed that exactly to the dysregulation probably of T-cells upon the viral reactivation and contemporary ability of producing antibodies. So I'm sure David was wondering if this is something that happened recently, or is something that is reported also by other groups.
Oh, thank you. The best answer I can give for your question is I'm going to punt it to Everett. who has focused a lot. Everett, you want to talk about post-transplant low-dose immune suppression with monotherapy for ORCA or 236 as opposed to TAC methotrexate?
Sure. Yeah, Robert, I'm happy to. So on these clinical protocols, the standard of care is methotrexate dose similar to the original dog studies, 1, 3, 6, 11, 9, 11. And then tacrolimus is generally targeted 8 to 12 nanograms per mil. With the ORCA graft or the Treg graft that we're using, we see that tacrolimus dose targets of around 6, so 6 to 8 are very effective. And there's a potential signal that it's very sensitive, immune reconstitution is very sensitive to that single agent tacrolimus dose. So that if you look at patients who dipped below 4 in their first 4 weeks, they actually have a higher risk of graft versus host disease. If you look at the patients who had a mean tacrolimus, despite our best intentions, greater than 10, they have mixed T-cell chimerism for longer. So it's very interesting because I think, as you're probably observing, the immune reconstitution can be really much more tighter when you engineer the cells and the cell numbers. And in general, a lot of the toxicity that we had seen previously, the severe mucositis, the shakiness, the headaches, the hemolytic complications are not really apparent. Although it's still not a large number of patients, it really looks, and Robert can attest, clinically, when you care for these patients, you're just not seeing these things.
Yeah, or high blood pressure even, yeah.
Great, thank you both. One more question for Dr. Lowsky from one of our fellows. Is there a potential role for different or individualized Treg T-con or Treg T-memory ratios other than 1:1 in studies like the Protocol 236 or the ORCA-T?
I just want to make sure I understand the question, thanks. We use a 1:1 ratio, and you're asking, can you get different ratios because some of this has to do with feasibility of isolating the right number of cells. That's how I'm viewing this question. You got to do it to find out how it works in humans, but you could always add more T-con. There's tons of T-con. You could always add more CD45 RA depleted total T memory, because those exist in the hundreds of millions per kilo. You're limited by how many Tregs you could add, and you're limited by how many CD8 memory you could add. And then, you know, you want to always be able to do the same thing. So you can't pick a high number where only like you can get it 60% of the time. So somewhere around 3 to 5 million per kilo, you know, for Treg, maybe as much as you can get. Everett could mention it. And I know 5 to 10 million per kilo for CD8 memory is you can't get higher. So if you want to do different ratios of non-Treg, non-CD8 memory, you're limited by that number, if that answers the question.
Which I think so, yes.
Well, but this is the beauty of Zoom. We've all decided it answers.
The fellow is around, so I'm sure that if the question was different, he will reach out to you directly.
Right.
Well, if there are no other questions or comments, I think we can close this section. And I really would like to thank both the speakers and Everett Mayer as a moderator for this other interesting discussion on the role of T-cell depleted transplant in adults. And I would like just to share a few slides as a conclusion of this day, which has been really rich. And I'm very, very happy on how it did go before to say bye to tomorrow. I just want to summarize what we heard today, because I think there are a lot of messages that we learned, starting from the keynote speaker, Yair Reisner, who really did a fantastic excursus on what is the history of the T-cell depletion, but also keep an eye on the future and on his next really plan of generating non-reactive memory beta cells from third-party donors. An exciting project that he's conducting at MD Anderson, and that I'm sure we will hear about in the next future. Jürgen Kubal talked mostly about the role of gamma delta T cells as tool for promoting graft versus leukemia after alpha beta haploidentical transplant, but he also reminded us how the use of targeted dose of both chemotherapy, such as busulfan and fludarabine, along with ATG, are really crucial to allow a correct expansion of the effector cells that we transfuse with our transplant. And he completed his talk mentioning new strategies of engineering T cells using gamma delta T cell receptor molecules to engineer alpha beta T cells and CAR T cell approaches as well. I don't like to talk about myself, so I will just show this slide to mention the discussion we had about what is the Stanford strategy that we are planning. And part of this is in collaboration with the adult group, as you heard in this last talk. Specifically, I show some data about the new clinical trial that we have ongoing, which combine T-allo10 cells with alpha beta T cell haplo depleted transplant and new preclinical therapies that we are developing in the lab. The second session was really very stimulating and about immune reconstitution. Susan Prokop started with reminding us how we have a really easy and very easily applicable a biomarker for evaluating the immune reconstitution, defined as the CD4 immune reconstitution by day 100. And she showed us some data that specifically in T-cell depleted transplant confirm the validation of this biomarker to predict the overall survival. In fact, you can see that in this big cohort that has been published on cytotherapy in 2020, even in the T-cell depleted settings, which in this case were CD34 positively selected graft, patients who had a CD4 immune reconstitution by day 100 had a better overall survival in comparison with those who didn't achieve the threshold of 50 CD4 per microliter by day 100. Very important connection that then really was present in all the other conversation we had today was the correlation between CD4 immune reconstitution and the exposure of ATG at the time of infusion of the stem cell graft. And specifically, these are data still not published, hopefully we can read them soon, about the correlation in a pediatric group of patients receiving CD34 positive selected graft between the AUC exposure of ATG at the time of stem cell transplant and the CD4 immune reconstitution. And you can see here that the immune reconstitution of CD4 is better when the AUC is below 20 in comparison with the other two groups that had a much worse CD4 immune reconstitution. But why CD4 immune reconstitution it is so important? Because there is a direct correlation with the no-relapse mortality overall in all the patients, but also on patients who develop graft versus host disease. So something to implement in our clinical activity. Andy January offered us really an overview of what has been the history of using T-cell depleted transplant in primary immunodeficiency in UK and specifically in Newcastle. They started to use alpha beta depletion back in 2012. But I think that the main messages that we got from Andy are really that most important is to transplant these patients without active infection, because this is really the main variable impacting the outcome. However, if we look at patients with SCID using alpha beta T cell depletion, they obtain an overall survival of 100%, which favorably compare with CD34 positively selected Marrow and the use of in vivo T cell depletion with Campa. Rightfully so, Andy was also pointing out that the TCR alpha beta depletion was started in an era where less toxic conditioning regimen and better supportive therapy was available. Different is the outcome for a non-skid PID, still really good considering that we are talking about a T-cell depleted approach with overall survival at 5 years of 70%, which is anyway better than the approach that published previously. And then Michael Mashan from Russia really completed this talk with his experience on naive depleted DLI after alpha beta haplotransplant. Of course, the goal of infusing these memory cells was to boost the immunoconstitution, reducing the risk of viral infection, and ultimately improving the leukemia-free survival. However, the results of multiple trials they ran and retrospective analysis in which they tested different doses of DLI didn't show what they expected. Specifically, although the DLI did not really cause excessive GvHD, they did not even prevent CNV viremia, and did not affect the incidence of relapse, at least in the cohort they evaluated. I have to say it was impressive, the non-relapse mortality that they presented, irrespectively to the use of DLI, 1% in one cohort and 3% of the other cohort. For both studies, the transplant were all first transplant, but really great data coming from this group. And now we just heard Wolfgang Bethge and Robert Lowsky talking about their experience in adult from the study conducted in Germany, a reduced intensity backbone for adult patients with very low number of alpha beta T cells in the graft and one short course, 30 days of MMF after the stem cell transplant infusion, who really demonstrated that even in the adult setting, the alpha beta T cell depleted haplotransplant platform is safe, translates in very low rate of both severe and chronic graft versus host disease, promoting graft versus leukemia thanks to the effector cells that are transfused adoptively with the graft. From Robert Lowsky, we had a nice overview of what is the BMT adult Stanford vision about T-cell depletion from the study infusing T-cons and Treg that really resulted in a marked reduction of acute and chronic graft versus host disease. The next generation of this project with the Treg and T-total memory with the ORCA approach that Everett Mayer presented at TCT last year, very low degree of grade 2 acute GvHD with this approach. And lastly, and I would say most importantly, again, a look on the future about what is the potential options that we have available. So what is ongoing right now, the infusion of CD8 memory T cells to really maintain low rate of GvHD, but promoting graft versus soma activity, and the idea of Robert of immunizing the recipient with tumor peptides that can really present the antigen to the CD8 effector memory T cells infused in the patient, and therefore help the expansion of these T cells and promoting their graft versus tumor activity. And with this, I hope that I was able to give you a quick summary of what this day represented. I am really very happy and grateful to all the speakers for their excellent talks, and really amazed by the number of people who followed us all day long. I'll see you tomorrow morning at 7:20 a.m. Pacific time for another exciting day in which we will hear a debate about two different strategies of T-cell depleted transplant, the alpha beta haplotransplant and another version of the CD45 array depleted. and Ken Cook will try desperately to defend the use of post-transplant cyclophosphamide in this arena of T-cell depleted people. And then we will have a very interesting session on what we call the innovative clinical pilot trials, what's new, what we are investing on, what we would like to see available in the near future for our patients. Thank you so much again, and I'll see you tomorrow. Bye.